Python ang complex. Oh, that's a shame. All right, I think we are now recording. Again, good morning, everybody. So some preliminary matters before we start discussing the new module. So your spokesperson, si Chazel, sabi niya on behalf of some of my classmates, aka orgmates, so shout out sa kanyang orgmates, I would just like to ask if it is okay to extend the deadline for the problem set 2. Of course, sige, dahil super bait ng Math 175 instructor nyo, kunwari, so sige, extend natin yung deadline. When do you want the deadline to be? The only deal is I can extend the deadline, but I will not move other requirements anymore, okay? So kasi sa Monday, meron na tayong lab exer concerning modules 10 and 11, so I cannot afford to defer it to next Monday, So yun na lang yung deal. Papahabain na pwede nating extend. Kailan nyo ba gusto? Kindly let me know in the chat box. So pero yun fix na yung ibang requirements or yung ibang deadlines. Uy, nahiya pa silang mag-request. Ito pala yung babawasan ko kasi usually ako yung nag-open up ng extension So, and I was checking my Canvas page kanina. Parang isa pa lang yung nagpapasa ng 2.2. Wala pa nagpapasa yata ng 2.1. Tapos I think last night, chinek ko yung 2.3. Tatlo pa lang yung nagsasagot. And siguro nawawala na yung prowess ko sa paggawa ng questions kasi lahat silang tatlo ay perfect dun sa objective part. So congratulations dun sa tatlo na perfect yung answers dun sa objective part. Oops, sorry, not video. Share screen ko. Tapos sabi ni CK, nakakalugi daw sa Python users yung crowd factorization, dinadrop ng program yung imaginary part. So that's a shame. But kindly see if Python, if there's a workaround sa Python, baka meron lang setting na kailangan palitan because I can't imagine Python not being able to handle complex numbers. Maybe there's a package or something that you can try to see na i-load para siya ay magamit. Or, pwede kayong mag-MATLAB, alright? So, yeah, ang powerful kasi ng MATLAB. Medyo nga lang, sayang kasi I am supposed to attend a MATLAB Expo, which is exploring the different packages of MATLAB, especially for data science, modeling, simulation, signal processing, image processing, voice recognition, artificial intelligence, ano pa kami nandun? Yung automated or self-driving machines. Kaya lang kasabay pala ng mga klase ko, so sayang, naka-register pa naman ako. But yeah, it's really an exciting tool yung paggamit ng MATLAB. And one parallel session that I attended yesterday is how to import and export things from Python and from TensorFlow para sa fluid dynamics, I think. So into MATLAB and vice versa. So it's very yung cross-platform ay maganda na. So kaya yun, nabigla ako na yung Python ay parang ayaw ng complex numbers or ng imaginary parts, okay? So kindly do that. Okay, so wala kayong suggestion when to extend the deadline? Will Sunday be enough or you want to do it Monday? Sige, pag hindi kayo sumagot ako na magde-decide. Yung release ng Exer, siguro ilalabas ko na siya by tomorrow. Kailangan ko kasing malaman kung gaano kahaba yung madidiscuss ko Charles. So, yung Lab Exer 4, for sure, kasama na doon yung Euler's method. So, if you have written a code para kay Euler's method, then that's fine. Just leave it there. Tapos magdi-discuss tayo ngayon ng Taylor's method. And then I'll see if we can tackle Runge-Kata methods on Friday. Tapos kung yon, siguro yung tatlong methods ay ipapa-implement ko sa isang IVP. Yes, Chazelle, the deadline would be on Monday. Okay, so dahil wala pa yung actual problem, what I suggest is you write the code. So hindi naman kasi nyo kailangan yung actual problem para magsulat ng isang code o isang routine para sa Euler or para sa Taylor's method. Okay, so you can do the programming right away, prepare all the code parts. Tapos sa Monday, i-input nyo na lang yung mga functions. So yung mga derivatives ng mga functions na ibibigay ko. But I'll make sure to give out the exer on, or the question for the exer tomorrow. Okay? And the deadline will still be on Monday. So no, kaya nyo ba ng Sunday yung problem set? Naubos na yung oras ko. 10 minutes na yung nakalipas. So maunguta ako ng konti. So, okay ba yan? Sunday deadline for problem set, or you want to do it Monday or Tuesday? Pero the deal is I cannot move the lab exer deadline on Monday. Sige na nga, Tuesday na lang. Okay lang ba sa inyo yan? Problem set 2 deadline on Tuesday, right before midnight, 11:59. But we do have a lab exer on Monday. Deadline ay Monday, right before midnight. Come on, guys. Okay, so Tuesday is this, okay? Grabe kung sinabi nyo Friday, edi Friday sana, wala, touch move na ako, nag-suggest eh. So just a couple of notes about this, okay? Partly kasalanan ko rin kasi may mga typo dun sa lab exer, dun sa problem set, because I wrote everything here from memory. So kaya medyo yung mga indexes ko ay medyo mali-mali. So paki-correct, for instance, 7, equation 7. So I already have it in the uploaded version. So though this is a specific example, tapos na-discuss naman natin yung development ng method para dun sa specific problem natin. I just want to clarify here that yung basis function ay a function of x, all right? So the integral or the moments, yung tinatawag nating moments, they are integrals with respect to the variable corresponding to the basis function. Okay? So ibig sabihin, mag-integrate to, mawawala yung variable ng index ng basis function. Ang matitira yung variable y, which is basically the variable on the right-hand side. Okay? So dapat walang subscript ito. Parang sa unang version ko ay x sub j yata ito. So wala tong subscript kasi yung x yung variable of integration. Wala tayong pina-plug in na value ni x. Nag-i-integrate tayo exactly nito with respect to x. Ang nilalagyan lang natin ng input ay si y. Kasi di ba i-discretize natin yung control region. So meron kang control interval, say A to B. Doon mo gustong i-match yung right-hand side. So ang gagawin natin, dahil hindi natin yun magagawa continuously, hinahati natin yung interval of consideration into a measure points, into a set of collocation points, y1 until ym. So nagbibigay tayo ng specific values dun sa mga y. Kaya nagiging constant itong integral na to. Kasi kung si y lang ito, so ang sagot sa integration na to is a function of y. Right? So, pero dahil si y sub j ay pina-plug in natin, si y sub j ay isa dun sa mga collocation points o test points na nandun sa discretization natin ng right-hand side. So this becomes a constant. So all the x will vanish after we perform the integration. So this guy is actually just a real number. And then the main fault I had when I wrote this first ay yung subscript. Napagpalit ko yung I at saka j. So yung j siya yung magbibigay ng row number. Kasi bawat isang y value or isang discretized value ni y, siya ay yung magko-correspond sa isang row. Okay? So yung mga rows na determine ng discretization ng right-hand side. Tapos, yung column number ay para sa pang-ilang basis function na yung kino-consider natin. Okay? So that's why this will be an m by n matrix where m is the upper bound for j. So kung ilan yung j mo, yun yung number of rows. Kung ilan yung I o ilan yung basis functions na gagamitin, yun yung value ni n. So that leads me to my second boo-boo dun sa problem 2.2b. All right? A 2020 yata yung nasulat ko, pero sinabi ko rito na yung matrix of moments ay 20 by 10. So dapat ang hanapin ko lang ay A sub 20 by 10. Okay? Unfortunately, hindi ko pa nagagawa yung answer key. So hindi ko pa masagot kung anong itsura, kung malalaki ba yung numbers na nasa laman ng matrix. So probably I'll answer you on Friday. So pakitanong na lang ako ulit, sir, wala bang clue dun sa laman ng matrix of moments? So paalala na lang, paalalahanan nyo na lang ako sa Friday para magkaroon kayo ng idea tama ba yung kinakapuntahan ng inyong exercise. Alright? So yun, let me see. Okay, so I think that's what I want to say about the problem set, aside from the deadline being extended to Tuesday, no? Sulat ko na lang dito. Deadline extended to Tuesday. Okay. All right, so now let's go to the actual purpose of today's lecture. Pupunta natin yung Module 11. So this is now available in Canvas, pero part pa lang kasi hindi ko pa nasusulat yung second part. The first part will be about Taylor's method, okay? So last time we looked at we reviewed what ordinary differential equations are, and we said ito yung mga equations na involve yung derivative. Tapos medyo kakaiba sila kasi ang purpose o ang goal natin ay makahanap ng isang function na nakakasatisfy ng differential equation. So we are not just looking for a solution that is a number or simply a vector of real numbers or complex numbers. So ang ginagawa natin ay naghahanap tayo ng function. Pero that's impossible to be done in a finite machine. So ang ginagawa natin, nagkaroon tayo ng discretization. So una, yung derivative, pwede nating palitan by a difference quotient. So di ba, ang derivative ay limit ng difference quotient. So instead of the limit, tatanggalin lang natin yung limit, magiging difference quotient lang siya. Yun yung discretized version. So yun yung tinatawag nating difference equation. And at that particular point, at the start of the derivation of any method, nakapag-introduce na kaagad tayo ng tinatawag natin na local truncation error. The local truncation error is the error incurred by translating yung continuous problem, which is finding the derivative, into a finite or discrete problem, which is computing the finite difference. All right? So yun yung local truncation error. Tapos, with the aid of Taylor's theorem, and assuming that that the function we seek, x has continuous first and second derivatives, naka-derive tayo ng Euler's method, which is a very basic and simple method. Okay? Na nangyayari ay hindi natin minamatch yung derivative sa buong interval because that's impossible. Ang ginawa natin ay hinati natin yung interval into several points, okay? So nag-consider lang tayo ng 5 points, 10 points, 20 points, or more number of points if the need be or if the need arise, okay? Tapos doon natin minamatch yung function values, alright? And sabi natin kay Euler's method, okay, that's good because both the local truncation error and the global discretization error are both of order big O of H. So, ibig sabihin, proportional, yung pagbabago sa step size o yung pagbaba ng step size sa pagliit ng error. So theoretically, if you want to get better accuracy in terms of LTE and the GDE for Euler's method, kailangan mo lang palitin yung step size. But hold on, hindi doon natatapos yung analysis. Kasi nga, pinaperform natin yung calculation sa isang finite machine. And finite machines truncate numbers, right? So hindi niya nakukuha yung, halimbawa, meron kang isang irrational numbers, hindi niya i-capture lahat ng decimal digits na nandun after the decimal point dun sa irrational number mo. So the computer, even for rational numbers, needs to cut the number of digits stored in its memory at kung saan niya ipe-perform yung calculations. Kaya nangyayari, hindi lang yung GDE at saka LTE yung nag-govern nung error, hindi lang sa kanya nakadepende yung error. There is some error that will come in from the machine. And I guess we did an analysis of that, and we have mentioned that we need to strike the balance between driving the GDE down, okay, by making H small, but not too small na magdo-dominate naman yung truncation error. Okay? So yun yung napag-aralan natin last week. So ngayon, titingin tayo ng mga methods na mas accurate kaysa kay Euler's method. Kasi si Euler's method, simple, maganda yung derivation, madali yung analysis. Kaya lang problema sa kanya, hindi siya ganun ka-accurate. It's just a big O of H yung kanyang accuracy. So if you want to get better results, kailangan nating ibaba yung step size. Pero pagbaba ng step size, tumataas yung truncation error due to machine precision. So hindi natin kayang ibaba talaga yung step size. And remember, pag binaba natin yung step size, dumarami yung points na kinoconsider. So dumadami yung calculations that we need to perform. And hence, kailangan natin ng mas efficient way, or I mean, not more efficient, but more accurate way of solving differential equations. And for that, we'll be talking about Taylor's method and the Runge-Kutta methods, okay? Para i-solve yung mga IVPs. Okay. So, yung Taylor methods, okay? So, dalawang classes to. So, una yung Taylor methods, pangalawa yung Runge-Kutta methods. So, yung Taylor methods, ito yung generalization ng Euler's method, okay? Kasi ang ginawa natin sa Euler's method, inassume natin na si function x na hinahanap natin has continuous first and second derivatives, right? Tapos, that allowed us to write it as a Taylor series. Tapos tinuncate natin yung Taylor series up to a certain number of points. In particular, tinuncate lang natin siya hanggang dun sa second degree derivative. Tapos pinalitan lang natin si t sub I ni psi sub I. Alright? So naging finite yung expression, and then from that finite expression, I think I wrote that here. Okay? So ito yung nangyari. Kung meron kang ganitong initial value problem, hindi ko pala sinulat yung Taylor's method. Pero I hope you remember it. Tinuncate natin siya hanggang dun sa x double prime of c na term. Tapos from there, we calculated what w sub I plus 1 is. Okay? Now, if you're thinking of what would be a better method, well, siguro sir, padamihin natin yung terms dun sa Taylor series expansion. Tapos yun yung tingnan natin, kaya ba nating ma-compute yung w sub I plus 1 o yung estimate para sa next time step using only known information like the previous estimate from the previous time step, some function evaluations, f, and so on. So yung titingnan natin. So ang idea ng Taylor methods, mas mag-consider ng mas mahabang Taylor series expansion para sa isang function x. Pero ang problema, the cost of doing that, we need to assume that x has more continuous derivatives. Dapat kung gusto natin na i-keep yung first n plus 1 terms dun sa Taylor series expansion, we need to assume that x has continuous first to n plus first derivatives. Okay? So yun yung gagawin natin ngayon para mabuo yung mga Taylor methods. Okay? Now, so again, we consider the IVP given in equation 11.1. Tapos, with this assumption, makukuha natin yung Taylor series expansion. The function x around t equals t sub I. So math 38 is waving. So ito yung ginawa niyo sa math 38. Taylor series expansion lamang. So ito yung makukuha natin. Tapos sabi ko, inassume na natin na continuous hanggang n plus 1 derivative ni x. So pwede kong putulin yung summation hanggang sa n plus 1 derivative and just replace what should have been a t sub I here by psi sub I, where psi sub I is a number between the observation time step t and the center of the expansion. So ito yung magbibigay sa atin ng error term. Okay? So kung matatandaan nyo, sa Taylor hanggang dito lang. Tapos ito, pinalitan ko na to. Hindi na to x double prime of t sub I. Ginawa ko na yung x double prime of psi sub I. Alright? Now, ang medyo problema lang dito, okay, so kung ikikip ko hanggang dito, so okay lang to. Ang gagawin ko kasi, plug in ko si t equals t sub I plus 1. Okay? So magiging t sub I plus 1 yan. So that's fine. This will be replaced later by w sub I plus 1. Kasi gusto nga nating i-approximate si x sub t sub I plus 1 by w sub I plus 1. Alright? So that's perfectly fine. I'll just plug in t equals t sub I. So this will be t sub I plus 1. So this guy will be the step size h. So again, for simplicity, we will assume that we have uniform step size all throughout the discretization of the time domain. Okay. So pag nag-plug in ako dito ng t sub I plus 1, ito ay magiging h. So ito ay mga powers lamang ni h, right? Hanggang h to the power n plus 1. Okay? Tapos, ano pa bang mangyari? Okay, so this is fine. This is x sub I double prime. Pero dito, magiging problematic to. Kasi what does this constant, or what is this constant? This constant is x double prime of t sub I. Tama? Per our notations. The problem is, do we know the exact value of x double prime of t sub I? We don't, right? Because we're looking for the function x. Hindi natin alam kung sino si function x. So, hindi natin alam si x prime. Hindi natin alam si x double prime. So, hindi ko mapaplug in yung value ng time step I dun kay x double prime to supply the needed value in this term. So, hindi siya agad-agad. Pero we can find a workaround around it, okay? Kasi kung matatandaan nyo, dun sa IVP, sinabi natin na all throughout the interval of interest, x prime is equal to f of tx. So that means, anong ibibigay niya sa atin? Si x double prime ay derivative lamang ni f with respect to t. All right? Now, I can write the derivative df over dt without the curly partials here, or hindi ako gagamit ng partials, kasi si f kasi talaga ay function lamang ni t. Yun nga lang, it is a function of t and another dependent variable x, but that dependent variable x depends on the variable t. All right? So essentially, pag sinimplify mo to, kaya mo pa rin niyang isulat as a function of t, kaya lang implicitly. Kasi si x ay hindi natin alam yung itsura niya. Ang alam lang natin si x ay binubuo lamang ng mga variables na t. All right? So the way to compute df over dt, kung natatandaan nyo sa Math 38, ay kailangan natin itong i-treat as the total derivative. And I hope you guys remember how to compute the total derivative. The total derivative is actually the partial of f with respect to the variable t. Okay? Partial yung gagamitin ko kasi si f kasi ay dalawa yung variables niya, x and t, even though x is a function of t, right? Plus df over dx, kasi si f ay function din ni x, right? Pero meron tong multiplier dapat na dx over dt, right? Kasi ang idea, ang palatandaan ko, para matandaan ko yung formula ng partial derivative, kailangan kong i-differentiate yung function with respect sa lahat ng variables na sa kanya, okay? Tapos dapat yung bawat terms nagsisimplify, quote-unquote, sa df over dt. Now, this is already df over dt, so I know that there is no other needed factor in here. Kaya lang ito, df over dx, kasi si f ay function ni x and t, so I need to take the partial of f with respect to x, all right? Kaya lang gusto ko, lahat ng aden dito nagsisimplify sa df over dt, all right? Kaya, so kailangan kong, alam ko na ito ay dapat kong i-multiply ng dx, ng derivative ni x, para mawala yung partial of x, sort of, right? Tapos ano ba si x? Si x ay function ni t. So, i-differentiate ko lang siya with respect to t. And nice enough, and this is nice enough because this simplify to df over dt. Tapos, dalawa lang naman yung variables kay f, so alam ko na ito na yung total derivative. Okay? Now, you might complain, sir, hindi ko alam si x. Paano ko malalaman si dx over dt? Well, that's fine because the IVP tells us that dx over dt is equal to f of dx. So, this guy will be replaced by f. Okay? So, ito yung ipapampalit natin dito sa second derivative. So, kailangan ko lang i-evaluate itong guy na to sa t as t equals t sub I and x equals x sub I. And that's going to be my replacement for x double prime sub I. Okay? Does that make sense, guys? Okay, maglala. Meron akong examples dito. Makikita natin paano nga ba computein yung mga total derivatives na yon. And then, if you want to get to use more and more terms, then sige, magdusa ka. Magko-compute ka ng mas maraming partial order total derivatives. Okay? So, halimbawa, Gusto mong isama si x triple prime. So, meron ka ditong x sub I triple prime. So, kailangan mong computein yung partial derivative si x triple prime, which will turn out to be the second partial of f with respect to t. Hindi pala second partial. The second order total derivative of f with respect to t. So, kailangan mo ito ngayong i-differentiate with respect to t ulit. And that will require using chain rule, addition rule, product rule, and so on. Kung ano mang rule ang kailangan sa pagde-differentiate. And that reveals the weakness of Taylor's method. Na kapag ka marami kang terms na kinip dun sa Taylor series expansion, magdudusa ka sa pagko-compute ng total derivatives. And the computation of the total derivatives can grow out of hand early. Kahit pa nga lang sa third derivative, pag medyo malas ka na ang komplikado ni function f, mahihirapan ka na mag-compute ng second total derivative niya. Okay? What more if you keep 100 terms? So that means you need to compute the 100th partial derivative of f with respect to the variable t. All right? So yun yung cons ng Taylor's method. There's a promise of a more accurate method, pero ang problema, mas marami kang work na kailangan gawin. Which is fair because there is no free lunch in this world. So you have to give up something para may mag-gain ka. Tipong ano nga to eh, ano nga yun? Law of equivalent exchange sa Full Metal Alchemist. So anyway, so that's the thing. So you need to do it for all terms. Sinabi ko na yan pala dito. Tapos, kapag ka na-expand mo na siya, so lahat dito ng mga higher order derivatives ni x ay papalitan ko na ng total derivative evaluated at t sub I, w sub I. Tapos, ito, papalitan ko na rin siya ng w sub I plus 1. So, ito ay magiging w sub I kasi wala tayong x sub I. Hindi natin talaga nakukuha yung eksaktong value ni w sub I. So lahat ng w sub I mapapalitan ng lahat ng x sub I mapapalitan ng w sub I. The estimate that we got from our previous calculation, right? Or from the previous time step. So ito magiging h, ito magiging h, ito ay magiging total derivative ni f with respect to t evaluated at t sub I, w sub I. Tapos ito ay magiging ito ay h to the k over k factorial. Then this guy will be k minus 1 total derivative of f with respect to t, evaluated at t sub I, w sub I, and so on. Okay. So plugging everything in will give us equation 11.3. Okay. So nangyari ay meron ditong w sub I, nilipat ko lang siya sa kabila, tapos divide both sides by h. Nakuha ko to. All right. So, ginawa ko lang yon para makita ko na ang local truncation error ng Taylor method, keeping the n terms, ay big O ni h to the what? Bakit kulang ako ng h? Probably I can just go back here and say that yes, the error incurred doon sa truncation nung Taylor series expansion ay power ni h to the n plus 1. Pero kasi i-divide natin all sides by h. So naging so ito yung error term, h to the n plus 1. Because remember, ito transpose ko dun sa kabila, tapos i-divide ko both sides by h. So ito ay madi-divide by h. So magiging big O of h to the power n na lamang. Oh, I remember it now kung bakit ganun yung nangyari dito. Ito yung ating formula para sa Taylor series of order n or para sa Taylor's method of order n. Bakit siya tinawag na order n? Kasi yung error term, kung hindi natin siya truncate, meron pa ritong plus h to the power n of n plus 1 factorial. evaluated times the nth derivative of x evaluated at an unknown number psi sabay. So ito yung error term. So dinrop ko siya, naging approximation ito. So iti-take note ko, yun yung error. And the error is actually of order big O of h to the power n. Kaya ang tawag sa method na to ay Taylor's method of order n. Kasi the promise is the error will vanish as fast as how h to the power n goes to 0. Tapos mas mabilis ito sa Euler. Kasi halimbawa pag si h ay si n ay equal kay 2, ibig sabihin magsimbilis na si h squared at saka yung error nagpupunta kay 0. Hindi katulad ni Euler na linear lamang yung relation, na kasing bilis lamang siya ni h sa pagbaba papunta sa 0 ng error. Okay? So that means if we are considering a Taylor method of order n, we need to compute until the n minus first total derivative of f with respect to the variable t. Okay. But since this is the error term in the translation of the problem from an infinite series to a finite series, ang tawag, ito yung tinatawag pa rin natin na local truncation error. Okay? So iba pa yung global discretization error na nakita natin last time, right? Though medyo komplikado yung pagde-derive ng GDE, I think the GDE for a Taylor method of order n ay big O din h to the power n. Pero I skipped the proof kasi medyo mahaba yung derivation and I want to keep this discussion a little light kasi nagpo-problem set pa nga kayo. So ito na lang. So yung LTE niya ay big O of h to the n. Possibly when we do the error analysis, we can see numerical evidence na yung GDE niya rin ay big O ni h to the power n. Okay? So that's the derivation of a general order n Taylor method. Okay? So in particular, this is the formula that we will use. So W sabay plus summation ng n. N nga ba? Oh, I think this should be hanggang starting from 2 ito dapat. Hold on. W sub 0. Tapos magkakaroon ka ng F, magkakaroon ka ng 0 dito. Okay, I think this is fine. Alright? So ito yung formula natin para sa Taylor's method of order. And ang palatandaan lang, kamukha lang siya ni Euler, pero mas dumarami yung terms na ginagamit. And bawat isang term mag-involve ng total derivative. So an order n method will involve until the n minus first total derivative of the right-hand side function f. All right? So let's make this concrete by looking at specific examples kasi baka nakakahilo that we are talking about abstracts dito. So specific example 11.1. We revisit this IVP that we had earlier. So sinolve natin to by Euler last time. So let's see, paano naman kapag second order Taylor method yung gagamitin natin. I'll keep the same step size, 0.5, okay? Tapos tingnan natin kung talaga bang mas maganda yung results na makukuha natin mula sa second order Taylor method because Euler's method is the first order Taylor method. Kasi when we take n equals 1 here, makukuha natin ay yung Euler's method. Okay? So, but here we'll take n equals 2. We're looking at the second order Taylor method para isolve itong problem na ito. So the right-hand side of the ODE will be our function f. So obviously it is a function of the independent variable t and the dependent variable x. Dahil second order Taylor method ito, kailangan kong computein hanggang sa unang total derivative ni f. Okay? So, kukunin ko yung total derivative ni f with respect to t. This is the formula that we have established before. So, we need to take the partial derivative of f with respect to t. So, this is our f. Pagpa-partial derivative, iti-treat lang natin lahat ng variables aside from t as constant. So, x is treated as a constant here. So, derivative of 1 is 0. So, mawawala yung derivative. Derivative ng constant times 1 over t is the constant times -1 over t squared plus partial of f with respect to x. So from this guy, we will treat t as a constant. So si x lang yung variable. So we'll have 1 over t as our partial of f with respect to x. And then times the function f, copy over lang yan. Okay? And then luckily, when I simplified this guy, oh, ang ganda na nangyari, 1 over t. All right? However, in the more generic cases, this partial derivative or this total derivative might involve both the variables x and t. Yun yung nagiging komplikado yung pagpa-partial derivative. Luckily for us, mukhang kaya natin itong extend into higher order Taylor method kasi ang simple lamang nung first total derivative. So yung mga susunod na total derivative, simple lamang din sila. Okay? So now I will use this information into equation 11.4 with n equals 2. Okay? So ito yung makukuha kong iteration formula. Not necessarily iteration formula, pero ito yung working formula natin para sa bawat isang time step. So remember, ang interval of consideration natin dito ay interval 1 to 6. We're told to use a step size of 0.5. So that means yung 1 to 6, hatiin ko into several points, na tigpa 0.5 yung pagitan mula sa isa sa isa. Tapos initial condition will be our W sub 0. So there is no error involved in there. And then I'm going to use that W sub 1 in order to get, to compute this right-hand side. Okay. Ang makukuha ko ay yung 2.125. And then the fourth column here, itong column na yan yung exact value. Kasi remember din sa introduction natin last Friday, ay kinompute natin yung exactong solution. So just to illustrate the errors, kaya kinompute natin yung actual solution. But in reality, you might not have access to the exabytes because you don't know what the exact solution is. Pero for illustration, kinompute ko yung relative error. And you see that all the relative errors are of order 10 to the minus 3. Na napakalaking improvement mula dun sa kay Euler's method. If I remember it right, sinulat ko yan dito. Ang average error kay Euler method ay 6.12%. However, ang average error dito ay hindi pa naka 1%, right? It's just 0.73%. The same thing goes for the L2 relative error. So now, to get a better visualization of how good this approximation is, ginraph ko siya. Okay. Galing sa second order Taylor's method, tapos yung exact solution, tapos kinompare ko yung Euler's method. Yung galing kay Euler's method, siya yung kulay purple. Okay? Tapos nakikita nyo, malaki nga pala yung gap mula dun sa actual solution. So, pero dito sa second order Taylor's method, makikita nyo na parang na sila, nag-overlap na talaga sila, right? So dito nga lang, medyo dito makikita natin yung difference, Pero pag nandito ka sa umpisa, oops, almost overlapping sila. And this is understandable kasi nagki-kick in na habang lumalayo ka dun sa initial time step, nagki-kick in na yung global discretization error. Kaya nga ang tawag natin doon ay global discretization error. And that happens because these values that we are using in order to get the values towards the right endpoint of the interval are accompanied by errors themselves. So ito, may error na yan. And kahit faulty siya o kahit erroneous siya pa rin yung ginamit natin dito sa pagko-compute ng susunod. So ibig sabihin, yung error dito ay may effect dun sa error dito. Tapos ito rin, yung errors mula dito sa unang 4, nakaka-apekto sila or nakakadagdag sila dun sa error dun sa panglima. Of course, absent some extenuating circumstances like cancellation of the errors being opposite in signs, so they added destructively, so gumaganda yung approximation. Pero it is conservative to assume na habang lumalayo tayo sa initial condition, malamang nagpropagate yung global discretization error. And that's what happened, I think, in here. Kaya makikita natin yung medyo pagde-deviate na nila habang lumalayo tayo doon sa doon sa left endpoint. Okay? So that's it. Okay. Now, sige. Push pa natin ng konti. Sige nga. Fourth order Taylor method. Now, kung fourth order Taylor method yan, kailangan ko hanggang third total derivative ni f with respect to t. Alright? Kaya lang, lucky tayo kasi yung first total derivative ay 1 over t lang. So, madaling kunin yung second total derivative ni f at saka yung third total derivative ni f. Alright? Kaya lang, kung minalas ka na si f ay napaka-komplikado, na yung total derivative niya ay napaka-komplikado, then it might not be easy to compute higher total derivatives. Okay? Pero for our case, this is good. Tapos, ipa-plugin ko lang sila dun sa equation 11.5. Makukuha ko tong iteration formula na ito. So, 1, 2, 3, 4, 5. So, we have 5 terms in here hanggang dun sa third order total derivative. Yung third order total derivative, actually, siya yung estimate para sa, siya yung fourth derivative nung function x. Right? So, kaya siya naging fourth order. Tapos pag in-implement ko ito kay MATLAB, ito yung makukuha ko. And you see now the errors are of order 10 to the minus 4. Okay. And there's a significant drop in the L2 relative error. Now the L2 relative error is 3.79 times 10 to the minus 4. Okay. Now, pag pinlot ko naman siya, kasi mas maganda lagi, mas madaling ibenta yung yung resulta ng iyong calculations o simulations pag may nakikitang pictures. Kasi ito, hindi ko ma-imagine okay, 10 to the minus 4, but I don't know what that means, alright? Pero pag pinakita mo yung graph, pinakamaganda yun ang galing dun sa Taylor of order 4. Kesa dun sa Euler, which now is the green line. Tapos medyo nag-overlap na rin naman sila. Yung purple ay yung second order Taylor, pero hindi ko na makita yung ano bang dapat kulay niya. Yung kulay red at yung kulay orange kasi almost nag-overlap na sila. Kahit nga dito, nakikita ko yung purple, pero hindi ko na masyadong ma-distinguish yung red dun sa orange. Kasi nga super nagano na sila, nag-overlap. Okay? And that's the promise of a higher order Taylor method. But again, it comes up at a very hefty price. You need to compute partial order derivatives. Now, is it worth it to compute more derivatives para lang mapababa yung error? Okay, and that's the next thing that I investigated. Kasi tiningnan ko, worth it ba na magano ko, paramihin ko? Hindi naman paramihin. Paano ko ba i-phrase? Ang kinompare ko kasi ay, of course, mas expensive yung higher order Taylor's methods. Lalo na kung i-fix mo si H. Halimbawa, meron kang, in our example, we have H equals 0.5. So that gave us 10 estimates, W sub I to compute. Hindi ko na binilang yung W sub 0 kasi si W sub 0, initial condition lang naman yan. Di tayo nag-compute dyan. Pero sa bawat isang time step dito, sa order for Taylor's theorem, gumamit tayo ng 4 na function evaluations. Ano yung 4 na function evaluations? We calculated f, its first total derivative, its second total derivative, and its third total derivative. So at every time step, we are performing 4 function evaluations. So ibig sabihin, in all, dito sa Taylor's method of order 4 with 10 time steps aside from the initial point, so we had a total of 40 calculations. Doon sa order 2 method, okay, ganun din, meron din akong 10 points, pero sa bawat point, kailangan ko lang mag-compute ng ilang function evaluations, f, and its first total derivative. So that just took me 2 operations, okay? So that's going to be 20 operations, almost half of what we required para dun sa order 4 method. Kay Euler's method naman, sa bawat isang time step naman, isa lamang yung kailangan nating i-compute. So basically, comparing these three methods with the same step size is not a fair comparison. Kasi si Taylor's method, napakatipid niya. 10 function evaluations lamang. Tapos si order 2 Taylor, tawagin natin siyang T2 para mas maikse, no? Si T2, parang Dota lang, bilang lang ng tore. Pero si T2, 20 yung function evaluations na pinerform natin. Meanwhile, T4 required us to do 40 function evaluations. So basically, it's not a fair comparison. We're like comparing apples to oranges here. Ano? So para makita na, baka naman dahil lang marami kang in-evaluate function evaluations na ginawa, kaya mas maganda yung T4 kesa sa T2 at saka sa Euler. Ang ginawa ko ay, sige nga, pagpare-parehasin ko sila ng step size, pagpare-parehasin ko sila ng number of calculations performed. So, ang ginawa ko rito ay, nasa na nga ba yun? Okay, here we go. Okay. Binalikan ko yung same problem, pero ngayon si Euler's method, sige, dahil matipid ka naman, isang operation lamang per time step, ano? So, bababaan ko yung step size mo. Gagawin ko ang step size mo ay 0.0125. Pag ito yung step size, there will be a total of 40 time steps. So, 4 na po na yung time steps kong gagamitin para kay Euler's method. So, if there would be 40 test points or time steps, isang operation sa bawat isang time step, so there would be a total of 40 operations. Now, kay T2, ginawa kong step size ay 0.25. There's going to be, this will result into 20 test points. Dahil 20 test points yan, pero kay T2, 2 function evaluation. Evaluate ko kasi si F at saka yung kanyang total derivative para makuha yung W sub I plus 1. Okay? So there would be a total of, again, 40 function evaluations then. Kay fourth order Taylor, sige, 0.5. Kinip ko lang siya kasi napakamahal ng bawat step ng Taylor T4. Ano? Kasi sa bawat step, 4 yung function evaluations na gagawin natin. So I will just keep H equals 0.5. So I'll have 10 points. Pero sa bawat point, 4 yung i-compute ko. Alright? Tapos nirun ko yung methods. Ano? Nirun ko yung methods, yung 3 methods. Tinali ko yung relative errors. Ano yung relative errors? Sa bawat isang T sub I kay Euler, ano yung relative error sa bawat isang T sub I ni T2 at sa bawat isang point ni T4. Mind you, magkakaiba na yung length ng time steps nila. Kasi ito, 4 na po yung time value, so meron akong 4 na pong relative errors. Ito, meron akong 20 relative errors. Ito, may 10 lang akong relative errors. Kaya I took advantage of MATLAB interpolating between 2 consecutive points para makita ko ng ganitong graph. Okay? So, walang error. Lahat sila kay t equals 1 kasi 0 yung error nilang lahat kasi fixed yon. Ano? Kung makita nyo dito, nag-start na kagad si Euler, yung blue yung galing kay Euler. Meron na siyang relative error dito. Kasi mas maliit yung step size niya, mas dense yung mesh, mas maaga siyang nagkaroon ng isang test point. Nagsimula siya sa 1.0125 yata. Tapos, and so on. So, kinonnect the dots ko lang yan para mas makita natin yung continuous na itsura ng graph. And you see here that Euler's method that had 40, the same number of calculations, incurred errors of order 10 to the minus 2. So, nasa below 10% yung error niya, between 1, actually mababa pa nga rito, pero it's about 1%. Okay? Pero si Taylor's method of order 2 using the same number of function evaluations, nandito naman yung error niya. Tapos ang nanalo pa rin sa pababaan ng relative error ay si Taylor's method, even if we just maintained 40 function evaluations to it. Now, this is not a completely fair comparison kasi Euler left the lecture. Hindi naman, kasi si Euler may pabida yun eh. Ang simple-simple yung calculation ko eh, compared naman sa inyo. Ano? Ito nga, i-depend ko na si Euler. So, relax ka lang, Charles. Ano? So, ang pwede maging argument ni Euler ay, unfair naman yan kasi hindi fair na bibilangin mo yung function evaluation kay F in the same cost as the function evaluation of the total derivative of F, right? Kasi remember, yung T2 at saka T4, kailangan mo yung partial, yung total derivative. dun sa counting na ginawa ko, medyo madaya. Kasi binilang ko as a single function yung partial derivative, ay yung total derivative ni f as single function. Hindi nga naman fair na pag napaka-komplikado ng nung total derivative ni f, say, of order 5, comparable ba yon sa evaluation lang ni f? Of course not. It's not fair, right? So, and actually, si Euler, ginagamit ko pa rin yan minsan. Kapag ka hindi ganun ka-sensitive yung application, ba sa engineering applications na may allowable naman na 5 to 10% error, then I'll go with Euler's kasi hindi ko naman kailangan magpabida-bida. I don't need to do more work. Pero kung nasa medical science ako, na it's a matter of life and death na yung calculation ko maging off by say 0.1% lamang, it can mean life or death of say a person undergoing remote or online surgery. So magti-T4 ako, magti-T5 kahit pa gaano kamahal yung pagko-compute ng partial derivative. So ganun yung nangyayari. Now, that comparison actually motivated the search for methods that will not require computing total derivatives. Kasi yun nga yung criticism of the Taylor methods. Kasi yung mga Taylor methods, or kung saan man may S, lagyan na lang natin parehas ng S para sure, Pero dun sa mga Taylor's methods, So, nagko-compute ka kasi ng total derivative. So, could there be some ways na we can have a higher order method without going through computing higher order derivatives, right? The answer to that would be the Runge-Kata methods. And that's what we'll do when we meet again on Friday, okay? So, any questions? Sakto pala yung lecture ko nagawa ngayon. Yeah. Good. Hindi nakalimutan ba ako? Okay. So, any questions, guys? So, I think ang labanan dito sa Taylor's methods ay pagalingan pagko-compute ng total derivative. So, if you have access to Mathematica, so pwede nyo siyang gamitin. Symbolic calculation siya. So, kaya nyo ipa-compute yung total derivatives kay Mathematica. So, kaya nyo i-simplify. So, gawin mo kay Mathematica. Kaya lang hindi magandang mag-program kay Mathematica. Kaya ang ginagawa ko, pag may symbolic calculation, kahit algebra yan or whatnot, papagawa ko siya kay Mathematica, ipapa-full simplify ko kay Mathematica. May isang time na meron napaka-komplikadong function na kailangang i-simplify. In-input ko siya kay Mathematica kaysa gawin ko siya by hand. Tapos natulog muna ako kasi matagal mag-run, napakahaba kasi talaga. So kinabukasan, pagkagising ko, meron ng simplified form. Parang 2 terms lang siya. Tapos yung 2 terms na yun yung in-incorporate ko kay MATLAB. So, kinopy-paste ko lang o in-import ko papunta kay MATLAB. So, it is really nice to have a cross-platform type of thing when doing these types of research. Okay? So, okay, may question si Charles. Actually, mas gamit yung Runge-Kata methods kaysa sa Taylor methods. Kasi nga, for most applications, and mas a logistic equation, I imagine kung meron kang logistic equation, yung right-hand side function mo ay rational na may logarithmic or may rational pa sa loob ng rational. Pag kukunan mo siya ng total derivative, napaka-messy na nung mangyayari. So even though you want to take advantage of the simplicity of the derivation of Taylor's method, so medyo mahirap mag-rely. Kasi every time that you need if you need to tweak your function a bit or your IVP a bit, kailangan i-recompute mo yung mga partial derivatives, and that will not be pretty. That will be very tedious and cumbersome, especially or actually even for small values of n. Okay? So kaya iwas ang mga tao sa paggamit ng Taylor methods. Yung Runge-Kata methods kasi, ang ginagawa niya lang ay evaluation lang ni f yung involved. Hindi ka nalalampas ng mga derivatives. I don't know I'm not familiar kung may gumagamit ng higher order Taylor methods, pero ako ay hanggang Euler lang o kaya hanggang T2 lang. Hindi ko na ina-attempt mag-T4. So kung kaya ni Euler na lang ako kasi mas simple siya. So, kahit sa optimization, Euler o kaya Newton's method, okay na yon. Hindi na ako nagpupunta sa mga mas advanced na Euler, Bayer-Stokes, na ganong methods. Okay na ako dun sa lower order. Especially for engineering applications. Kasi buti na lang sa engineering applications ako nagwo-work. So 5 to 10% error is still good for them. So, pero kung sa math, maarte kasi yung mga taga pure math, so kasi ang errors na gusto nila, 10 to the minus 6, 10 to the minus 8, and so on. Okay? So, all right. So, other questions? Sorry guys, I need to jump to another meeting at 1 p.m. Medyo lagari ngayon, tapos may meeting uli ako from 1:30 to 3. So, okay. So, I hope everything is fine. So, let's meet again on Friday to answer probably some of the questions that you might have hanging. Probably including also the problem set. But until then, guys, keep safe and kita-kits na lang ulit. Bye!
Thank you po, sir.
All right, salamat din.